Welcome to Theory of Computation. This is lecture number 6. In the last lecture, we looked at many examples of Turing machines, and then we looked at a lot of variants of Turing machines. We then showed that adding more tapes or more heads to a Turing machine does not actually add to the power of the Turing machines, in the sense that a single tape Turing machine can recognize exactly the same languages as one which has more than one tape, say 50 or 100 tapes. We also looked at another model of computation last time, which we called enumerators. In the last lecture, we showed that enumerators enumerate exactly those languages which are recognized by Turing machines. So in some sense, both these models are equivalent. The outline of today's lecture is as follows. Today we will prove the equivalence of enumerators in Turing machines more formally. Once again, we'll explore this technique called dovetailing, which is very important, and we will be using it throughout the course. After that, we will formally define what an algorithm is. We will discuss the churchturing thesis, and then we'll talk about encodings. And in the last part of the lecture, we will talk about Hilbert's 10th problem and Malthus Theorem. So let us start by discussing enumerators. As you will remember from the last lecture, enumerators are machines which do not take any input. There is a work tape and there is an output tape. When you turn on an enumerator, what it does is it starts calculating or computing by using its work tape, and every once in a while it writes something on its output tape. The output tape is write only. The enumerator only uses it to write its output. When we run an enumerator, it starts writing strings on its output tape, and the language enumerated by that enumerator is the set of all strings that are eventually written down on the output tape. Let us define these concepts more formally. How would we define an enumerator? Well, by now we should be used to it. We have formally defined many different kinds of machines. For example, we've defined Turing machines, we've defined two-tape Turing machines, and so on and so forth. So by now, it should be reasonably easy for us to formally define exactly what an enumerator is. An enumerator formally is going to be specified by the following things. An enumerator E is equal to Q, sigma, gamma, Q naught, and delta. Here Q is the set of states, sigma is the output alphabet, and hash and box are not elements of sigma. So the hash sign and the blank do not belong to the output alphabet. Gamma is the work alphabet for this enumerator, and it contains the blank symbol. Q naught is the start state, and the most important part of the enumerator which we have to specify is the transition function, which will tell us how the enumerator works. Let us think about what this transition function will look like. Well, what are the decisions that we have to make? An enumerator is reading a symbol from its work tape, and it's in a particular state. So the domain of the delta function is going to be Q cross gamma. Q is the set of states, and gamma is the work alphabet. Now, what are the decisions that the enumerator has to make? Well, first of all, it has to decide what symbol it will replace the current symbol with. The second thing it has to decide is what will be its new state. The third thing it has to decide is whether it will move left or right on the work tape. So, the range of this function is going to be Q, which will specify the new state, cross gamma, which will specify the new symbol to be written, cross L or R. This completely determines what one of the heads does. But an enumerator is also supposed to produce an output. So we have to also specify what the output head does. Therefore, in the range of the delta function, we have also included gamma union epsilon union the hash symbol. That means an enumerator in a state reading a particular symbol on the work tape can decide to either produce an output, which will be a single character, or produce epsilon, the empty string, which means it doesn't produce an output. So delta, the transition function for a enumerator is, delta is a function from Q cross gamma to Q cross gamma cross LR cross sigma union epsilon and hash. So this is complete specification of what an enumerator is. Let us now talk about how a configuration of an enumerator looks like. Well, if an enumerator is in a certain configuration, what are the things you have to specify in order to tell me what the enumerator exactly is doing at that time? First of all, you have to tell me what the state is, what is written on the work tape, which symbol is being scanned on the work tape. You also have to tell me what is the output that has been already produced by the enumerator. So a configuration of an enumerator would be of the form alpha, Q, beta, comma, W1, hash sign, W2, hash sign, all the way up to WK, hash sign, followed by an X. Here, alpha and beta are going to be strings over gamma star, whereas X is going to be a string over sigma star, union sigma star followed by a hash. Essentially what we are saying is, you have to tell me what is written on the work tape, which state the enumerator is in, what is the current work symbol that it's reading, followed by, you have to tell me what are all the contents at the output tape. Notice that the output tape, the enumerator is only allowed to write symbols of the output alphabet on the output tape. And when it's in the middle of outputting a string, there will be no hash sign following it. But when it has successfully outputted a complete string, it would have a hash sign at the end. So this is what a configuration of an enumerator is. Similarly, we will have to define concepts that we did for Turing machines. So for example, I've left it as an exercise for you to define the yields relation for an enumerator. Let us look at another definition. We will say that an enumerator E outputs a string W if it reaches a configuration which is given by alpha, Q, beta, W1 followed by hash sign, followed by W2 all the way up to WK, followed by W, followed by a hash sign. You will notice that I've been very careful in defining the string that is enumerated by an enumerator. What I'm saying is that for me to say W is enumerated, the enumerator must enumerate the string W and then put a hash sign after that. Let's see why I'm doing this. Let's take an example. Suppose an enumerator has written 00 on the output tape. I cannot claim that it has outputted the string 00 because it may be in the middle of outputting another string 001. But once it has outputted the string 00 followed by a hash sign, then I can safely say that the enumerator has actually enumerated the string 00. What is the language enumerated by this enumerator? Well, the language enumerated by this enumerator by definition is the set of all strings that it ever writes down on its output tape. So you may think of an enumerator as a device that outputs strings from a given language. There are a few things that you must ponder about. Firstly, we do not require that the enumerator enumerates strings from a given language in any orderly fashion. So we are not saying that all the smaller strings of smaller lengths should be enumerated first and then strings of larger length should be enumerated. That's not a requirement. An enumerator may be enumerating some very small strings and then it may enumerate an extremely long string in the language and then get back to smaller strings again. The second thing that you have to notice is, suppose that the language L is infinite. Then if an enumerator enumerates the language L, it will never actually finish the job of writing all the strings on its tape because that would take infinite amount of time. However, we require that every string must eventually appear on the tape. Let's think about it more carefully. Suppose I were to tell you to write down all integers. Well, you can start writing 1 followed by 2 followed by 3, and you know how to count, and therefore you can start a process whereby you're writing one integer after another. Of course, you will never be done. But suppose I'm waiting for some integer to appear in your list. Say I'm waiting for 55,000. Then after some number of steps, eventually you will write 55,000. So an enumerator, given any string in the language L, eventually enumerates that string. Last time we said that enumerators enumerate exactly those languages which are recognized by Turing machines. Let's look at that theorem. A language L is Turing recognizable if and only if some enumerator enumerates it. So we have two things to prove in this theorem. We have to prove that if a language is Turing recognizable, which means that if I can make a Turing machine that recognizes strings of that language, then I can also make an enumerator that enumerates that language. Similarly, I have to prove that if there's an enumerator that enumerates a given language, then I can make a Turing machine that would recognize exactly the strings that are enumerated by the enumerator. One part of this theorem was very easy. That is, if you give me an enumerator that enumerates a given language, then I can make a Turing machine that recognizes exactly the same string as the ones that are enumerated by this enumerator. Conceptually, the idea was that this Turing machine will take an input x. Now what it would do is it will turn this enumerator on, and every time it outputs a string, it will compare that string with x. If that string is equal to x, then the enumerator has outputted x and the machine will accept. Otherwise, it will simply continue. Let's look at the formal proof. Let L be a language enumerated by E, then L is a Turing recognizable language. To prove this, we are given an enumerator E that enumerates L. We have to show that some Turing machine M accepts L. The informal description of this Turing machine is as follows. The machine gets some input x. What it does is it runs the enumerator E, and each time the enumerator outputs a string W, it would check to see if W is equal to x. If W is equal to x, then the machine goes into the accept state, otherwise it continues. So it will wait for the enumerator to enumerate another string. So this was conceptually very easy. All you have to do is run the enumerator and wait for the string x to appear. If the string ever appears, you can accept. Otherwise, you will never halt. So this Turing machine will recognize exactly those strings that are enumerated by this enumerator. The other part is not so easy, and it required us to develop a new technique called dovetailing. Let's see what we have to prove. In this case, we have to prove that if we are given a Turing machine, we can make an enumerator that enumerates the language of that Turing machine. Well, we started with one simple idea, which is wrong, but let's think about it first and see why it is wrong. Suppose what we do is we take the strings in lexicographical ordering. Remember the lexicographical ordering, the strings come like epsilon, 0, 1, 0, 0, and so on. And for each string, we run the Turing machine on that string to see if that string is accepted by that Turing machine. If it is accepted, we can simply output it. So the description of this enumerator formally is given as follows. For I equals 1, 2, 3, and so on, what we do is we simulate the machine M on xi. Remember here, xi is the ith string in the lexicographical ordering. If M accepts xi, we simply output xi on the output tape. Well, what is wrong with this proof? Let's look at one example and see what is going wrong. Suppose that I have a Turing machine which accepts epsilon, rejects 0, accepts 1, and loops forever on 0, 0, but the machine also accepts 0, 1. In this case, this particular enumerator that I have described will never enumerate the string 0, 1, because it will enumerate the string epsilon. Because the machine accepts epsilon, then it will run m on 0, and the machine rejects 0, so it does not enumerate the string 0. So far, so good. Then it runs the machine m on 1, and the machine accepts and it enumerates the string 1. That's very nice. But when it tries to run the machine m on 0, 0, the machine loops forever. So since the machine loops forever on 0, 0, therefore this poor string 0, 1 never gets an opportunity. And therefore it is never enumerated by the enumerator. So this enumerator enumerates a language which is actually a finite subset of the language which is accepted by the Turing machine M. So how did we get around this problem? We use this technique called dovetailing. The basic idea is that since we have a machine, a Turing machine, and we don't know whether it will accept or reject or loop forever, we should not invest all our time on one string. So we will essentially, you can think of it as time slicing. We are going to give each string a certain amount of time, and if that string is not accepted in that finite amount of time, we'll go on to the next string. But once we have done that, we'll come back to this string and give it a little more time. So this way we will never get stuck. So let's look at this technique formally. So formally, this new enumerator is defined by the following description. The solution is called dovetailing. As you can see, we have an outer loop where I is going from 1, 2, 3 and so on, which never ends. However, the inner loop is a finite loop because j goes from 1 up to I. So for every I, the inner loop is going to execute a finite number of times and therefore is guaranteed to stop. And essentially what we do is we simulate m on the string xj only for I steps. So if I is equal to 5, we will simulate m on x1 for 5 steps, m on x2 for 5 steps, all the way up to m on x5 for 5 steps. So all these simulations are going to end, and then we'll come back to an increment or I, which will become 6 and so on and so forth. Now if m accepts xj in any of these runs, then we will output xj. So this way we never get stuck on one string. Let us see why this is a proper solution. In this case, what we have to show is that if a string is accepted by m, then it will eventually be outputted by this enumerator e. Suppose you have a string xt which is in L. Then m accepts xt and it must accept xt in some finite number of steps. Let's say that this number of steps is k. Then we claim that if I take I is equal to the maximum of k and t, then the string xt will be outputted when I reaches t. Well, this is because m is simulated on the strings x1 up to xi in the ith step, and since I is greater than or equal to t, hence xt happens to be one of these strings. So m will be simulated on xt for I steps. Also, since I is greater than or equal to k, hence the machine m will accept the string xt in k steps. So when I reaches this value, then xt will be outputted by this machine. So we have just realized that all strings in the language will be eventually enumerated by this enumerator. We have one minor point to discuss, that is that only strings in the language will be enumerated by the enumerator and no more. That's quite easy to see because the enumerator only enumerates a string after it has been accepted by the Turing machine M. Therefore, that string must be in the language accepted by the Turing machine, and therefore any string that is enumerated by this enumerator is in the language. Hence, this enumerator enumerates all strings and only the strings that are in the language L. If you think about this enumerator, there is something that is slightly distressing about this enumerator, that it will enumerate a given string many, many times. In fact, if you think about it, if a string happens to be in the language L, then it will be enumerated by this enumerator infinitely many times. So you may ask if we can design an enumerator that will only enumerate each string of the language exactly once. Well, that's not going to be hard. If you intuitively think about it, what we can do is, before enumerating a string on the output tape, we can maintain a table of all the strings that we have already enumerated, and instead of enumerating a string, we can simply check that table. If that string has already been enumerated, we will not enumerate it again, but if we don't find it in the table, we will output it and also save it in the table. So a very simple exercise for you is the following. Show that if L is a Turing recognizable language, then there is an enumerator E that enumerates the language L. Furthermore, each string of L is enumerated by the enumerator exactly once. This exercise is not very difficult, and you should be able to do it without much problem. Let us now talk a little bit about what we have achieved by studying Turing machines and defining them. Well, the intuitive notion of what an algorithm is now the same mathematical notion of a Turing machine. So we have been able to define what an algorithm is. An algorithm is a Turing machine that always halts. Said in another way, an algorithm is a decider. It's a Turing machine that halts on all inputs. It either accepts the inputs or rejects the input. So now, the mathematical notion of a Turing machine has helped us capture the intuitive notion of an algorithm. This is the very essence of church-turing thesis. The church-turing thesis asserts that the intuitive notion of algorithms is equivalent to that of Turing machines. Put it another way, if we are thinking about intuitive algorithms and we're thinking of models of computations, then a Turing machine completely captures all possible algorithms that we can think of, or all possible algorithms that can be implemented on reasonable machines, on machines that we can actually build. By doing this, we have been able to define an extremely difficult concept, the concept of a process that stops after finite number of steps. And this now allows us to study very, very difficult questions. Questions like Hilbert's 10th problem. Remember from the first lecture that Hilbert had asked us to devise an algorithm for a given problem. Well, now what we are looking for is a Turing machine that solves Hilbert's problem. The church-turing thesis is extremely important, and it says that we have been able to find the ultimate model of computation, or we've been able to completely capture the definition of an algorithm. As I have told you before, the church-turing thesis is not a theorem. It's simply a thesis, and therefore it doesn't have a proof. However, it is the most widely accepted thesis in computer science. All computer scientists and all serious computer scientists that I've ever met in my life believe in the church-turing thesis and feel that it's a reasonable hypothesis, that we have been able to capture the definition of an algorithm in the very concept of Turing machines. Let us now discuss another very interesting topic which we will be needing throughout this course, and that is of encodings. Note that we always take inputs to be strings over some alphabet sigma star. Suppose that sigma is equal to A, B, C, D. However, as computer scientists, we're more interested or more comfortable with the natural alphabet that consists of only two symbols, zeros and ones. Well, what can we do? We can agree that we will map A to 0, 0. That means we will encode the symbol A in sigma as 0, 0, B as 0, 1, C as 1, 0, and D as 1, 1. In this way, we can encode any alphabet into the alphabet 0, 1. Note that this mapping will also encode strings over sigma star to strings over 0, 1 star in the natural way. The encoding of a string is obtained by encoding each of its characters and then putting them together, concatenating them together. Mathematically, the encoding of W1 followed by W2 up to Wn will be given by the concatenation of the encoding of W1 followed by the concatenation of the encoding of W2 followed by the encoding of W3, and so on. Now suppose that you have a language over some alphabet sigma. So L is a subset of sigma star. Well, we can encode the alphabet sigma into our binary alphabet. Similarly, what we can do is we can define another language, L sub E, which is the set of all encodings of strings in the language L. So L sub E is the encodings of W, where W is in L. This language is now a language over the binary alphabet. This tells us that all problems which are posed over some other alphabets can easily be posed over the binary alphabets via encodings. Actually, it's equally difficult to design a Turing machine for L. It's as compared to designing a Turing machine for L sub E. As computer scientists, we want to solve interesting problems, and usually the input to our problems is complicated objects like graphs or matrices or even images. However, the definitions we've made only allow us to pose problems in terms of strings, and that seems very restrictive. However, this is not the case, because as computer scientists we know that all the objects that we deal with can be expressed in terms of 0-1 sequences, so they can all be posed as problems over the language 0-1 star. Let's look at a few examples to clarify this notion. Suppose I am interested in the set of all pairs of integers I, j, such that I squared is equal to j. So L is a language which consists of pairs I comma j such that I squared is equal to j. So certain pairs which are in this language are 1, 1, 2, 4, 3, 9, and so on. And pairs of integers which are not in this language are 1, 3, 2, 5, 3, 1. They do not belong into this set. This is a subset of natural numbers cross the natural numbers. Now, suppose you ask somebody to recognize these pairs of natural numbers. Well, this is not a computer science problem unless we actually specify how pairs of natural numbers will be encoded as a string. Let's look at one particular way of encoding pairs of natural numbers. Since we are encoding only pairs, what can we do to encode these pairs into strings? Let us say that we reserve 1, 1 to represent 1, 0, 0 to represent 0, and 0, 1 will be used as a separator. Then we can encode 2, 4 as follows: 1, 1, 0, 0, 0, 1, 1, 1, 0, 0, 0, 0, 0, 0. The first 4 characters is actually 2 written in binary, but we have repeated 1 and 0, and therefore it has length 4. The next string 0, 1 is actually saying that this is where the next number is starting, and then you can clearly see the binary representation of 1. However, each digit is repeated twice. This is a very natural way to encode a pair of integers. Of course, there can be other more efficient ways of encoding. We are not going to get into this discussion, but the major point is that pairs of integers can be encoded into strings of zeros and ones. So we can define this new language L prime, which is the encodings of all pairs ij such that I squared is equal to j. This is now a language over 0, 1 star. This tells us that we can take a very sensible question and convert it into a language over our favorite alphabet 0, 1 star via encodings. In fact, that's what we always do in computer science. As computer scientists, you know that any kind of complicated input eventually becomes a sequence of zeros and ones. Let's look at another language. Let's look at another problem. Suppose we are interested in matrices which have integer entries and whose determinant is not 0. So we are interested in invertible matrices which have integer entries. How can we pose this problem as a problem over strings which are made of zeros and ones entirely? So what we will have to do is come up with a way of encoding matrices into strings of zeros and ones. How can we encode this problem so that it becomes a language over 0, 1 star? Let's say we have the matrix which is, the first row is 2, 5, the second row is 3, 6. What we can do is first write this matrix linearly, that is also called row major order. So I can represent this matrix as 2, 5, 3, 6. Now we can write down all the numbers in binary where 0, 0 represents a 0 and 1, 1 represents a 1 and 0, 1 represents the separator comma. So the encoding of this matrix becomes 1, 1, 0, 0 and so on. And as you can see, this encoding is quite complicated, quite long. However, conceptually, it's not difficult at all. So now we can define the problem as a language over 0, 1 star as follows. What we want to do is to collect all the encodings of matrices whose determinant is non-zero and whose entries are integers. So more formally, the language L prime is given by the encodings of A such that A is an n by n matrix with integer entries and whose determinant is non-zero. Let's look at another example. Suppose we are interested in graphs. We are interested in solving some problems about graphs. Can we encode all graphs as 0, 1 sequences? Well, let's just do a simple example and see how that would be done. Here is a picture of a graph, and as you can see, the node 1 is connected to the nodes 2, 3, and 4. The node 2 is connected to just the node 3 and 1, and so on. How can we encode this graph into a string of zeros and ones? Well, what we can do is first try to write this graph linearly, and this can be done by writing down the list of vertices followed by a list of edges. So the linear representation of this graph becomes 1, 2, 3, 4 followed by the pairs 1, 2, 2, 3, 3, 1, 1, 4. This linear representation can be easily converted into a string of zeros and ones via encodings. Let's see how this is done. Suppose we agree that 1, 0, 1 represents the right bracket, 1, 1, 0 represents the left bracket, 0, 1, 1 represents the separator comma, 3 consecutive zeros will represent 0, and 3 consecutive ones will represent 1. Now it's easy to encode the whole graph. Each number is simply encoded in binary, and the whole encoding of this graph turns out to be the long 0, 1 string that is written on the screen for you. As you can see, this string is very long, even for a very small graph. And it looks very complicated, but conceptually it's very simple. You can simply go through this string and decode the graph. Similarly, if I give you a more complicated graph, you can very easily convert it into the new representation and write down the 0, 1 string that represents this graph. This way we can ask interesting questions about graphs. However, all these questions will be languages over our favorite alphabet 0, 1. Let's look at an example. Suppose we define L to be the set of all graphs such that G is a connected graph. Well, we can instead look at the computational problem L prime, which is the set of all encodings of graphs which are connected. And now we can ask this whether we can make a Turing machine that recognizes this language L prime. What I have told you about encodings should not be surprising to you at all. As computer scientists, you know that all objects that we deal with in computer science are eventually represented with sequences of zeros and ones. If you have an image or a graph or a sequence of numbers or matrices, eventually everything inside a computer is represented by zeros and ones. So encodings will allow us to ask very interesting questions about graphs, matrices, and other mathematical objects. However, what we will do is first map these objects to 0-1 strings and then solve those problems in the language of strings. So we will be looking for Turing machines which are only accepting languages over 0-1 star, and we will be encoding all our objects into these strings. Recall from the first lecture that we had discussed Hilbert's 10th problem informally. Well, now we have formalized many things. We have discussed what languages are, what strings are, what Turing machines are, what a decider is, and therefore now we know precisely what an algorithm is. So now we are in a position to discuss Hilbert's 10th problem more formally or more precisely. Let's look at Hilbert's 10th problem. Hilbert's 10th problem was about Diophantine equation. Let us cast it in the modern language. The problem says, devise an algorithm that would decide if a multivariate polynomial has integral roots. Well, we had discussed what multivariate polynomials are. A multivariate polynomial is a polynomial over several variables. An example of a multivariate polynomial is given to you on the screen. It's 6x cubed yz squared plus 3xy squared minus x cubed minus 10. So Hilbert is asking the following question. He's saying, can you devise an algorithm which will take an encoding of a multivariate polynomial and tell us whether the polynomial has integral roots? So in the formal language, Hilbert's language will be defined as follows. H is given by the encodings of all those polynomials such that the polynomial P has integral roots. Here once again, the angle brackets are saying that we'll encode the polynomial in some way. There can be many ways of encoding polynomials, and it is your exercise to find at least one way of encoding polynomials. So Hilbert's 10th problem formally and in our language is given as follows. Is there a Turing machine M that halts on all inputs and the language of M is exactly equal to H? So now we have exactly defined Hilbert's 10th problem as a language, and we are asking if there is a Turing machine which accepts this language and halts on all inputs. Since Turing machines are an exact concept, not an intuitive one, it's an exact mathematical concept, it's an exact mathematical object, therefore the answer to this question would be yes or no. Either there would be a Turing machine which accepts this language and halts on all inputs, or there would not be such a Turing machine. We cannot have any shades of gray when we are answering Hilbert's 10th problem. That's because we are not looking at the intuitive notion of algorithms, but a very formal notion of Turing machines that halt on all inputs. Well, as I had told you earlier, Hilbert's 10th problem was solved in 1970 by Yuri Matissevic. So now we are in a position to understand Matisevic's theorem. This theorem is by Yuri Matissevic, 1970, and he states that H is not decidable. There is no Turing machine M that halts on all inputs with the language of M equal to H. So Matissevic eventually proved that there is no Turing machine with which you can solve Hilbert's 10th problem. Thus, the process algorithm that Hilbert was asking for does not exist. Unfortunately, we will not be able to prove Matisevic's theorem in this course. And the reason for that is, to prove Matisevic's theorem, we have to understand Diophantine equations, which requires us to understand a lot of number theory. And this is not a course in number theory, this is a course in computability and complexity theory. However, we will prove many theorems that are like Matisevic's theorem. The only difference would be that the language in question will not be Hilbert's language, it will be some other different language. So we will take some languages and we will show that there are no Turing machines which accept that particular language and halt on all inputs. Let us now look at a simpler problem. Let's define H1 to be the set of all polynomials in one variable which have integral roots. So formally, H1 is the encoding of all polynomials in one variable, say x, and those polynomials have integral roots. Let's see if H1 is Turing decidable. Let's see if we can make a decider that accepts this language H. Well, let us first observe that this language is Turing recognizable. That is, we can make a Turing machine that will accept all polynomials that have integral roots. Here is a description of a Turing machine that does exactly that. On input P, where P is a polynomial, the Turing machine runs this infinite loop where I is going from 0, 1, 2. What it does is it evaluates the polynomial on x equals I and x equals minus I. If this polynomial evaluates to 0, it accepts. Otherwise, it continues and goes on to the next value of I. As you can see, this Turing machine will accept all polynomials which have an integral root. However, if they don't have an integral root, and if I give an encoding of such a polynomial to this Turing machine, the machine will loop forever and never produce an output. It would never reject a polynomial. On the other hand, all polynomials that have an integral root will be accepted. It is your exercise to actually prove that you can make a Turing machine which decides this language, in the sense that it would accept all polynomials that have integral roots and it would reject all polynomials that do not have integral roots. This language H1 is much simpler than Hilbert's original language. Our next topic would be how will we describe Turing machines in this course. There are three ways to do it. One is a formal description of a Turing machine. The second is what we'll call the implementation description of a Turing machine. The third will be a high-level description of a Turing machine. Let us look at a few examples of how this is done. As you remember, in the earlier lectures, I had insisted on describing a Turing machine by specifying all the 7 things that are needed for it, namely Q, sigma, gamma, Q naught, Q accept, Q reject, and the transition function delta. That is the formal definition of a Turing machine. So to describe a Turing machine formally, you must specify all these 7 things. And when you have done so, you have given a formal definition of that particular Turing machine. On the other hand, it's very cumbersome to describe Turing machines by formally defining them. Transition diagrams for Turing machines that solve any practical or useful problem have hundreds, if not thousands, of states. And by looking at transition diagrams, we hardly get any intuition about what the Turing machine is doing and how it is going about solving the problem that it's trying to solve. On the other hand, we can use another way of describing Turing machines, which we will call the implementation level description of a Turing machine. In such a description, we will actually talk about the tape and how the head moves on the tape and how it performs various small tasks in order to accomplish something more complicated. Well, we have already looked at some implementation level descriptions of Turing machines. Here is one example. Suppose that you have a language L which is W followed by hash sign followed by W, where W is in 0, 1 star. How can we devise a Turing machine to recognize this language? Well, you can come up with a formal description which will be quite complicated. However, I feel that the following implementation level description will convince you that there is a Turing machine which recognizes this language, Let's look at the implementation level description. The machine will scan the input first and make sure if it is of the form W1 hash followed by W2, where W1 and W2 are in 0, 1 star. In other words, the machine will make sure in the first pass over its tape that there is only one hash symbol on the input tape. In the second phase, the machine will zigzag over the input, matching each symbol of W1 with one symbol of W2. If all the symbols match, then the machine will accept. If any symbol fails to match, the machine will reject. As you can see, this implementation level description of this Turing machine is not a formal description, but it convinces us that if we were to sit down and spend time over this description, we will be able to convert it into a formal description. Well, for the rest of the course, we are not even going to describe Turing machines at this level. What we would prefer is what is called high-level description of a Turing machine. And in this case, a Turing machine will simply be described by giving an algorithm. We have already used these high-level descriptions. But just to make it clear what a high-level description is, let's look at one more example. In a high-level description, we do not refer to tapes or heads of the Turing machine. We simply describe the Turing machine as an algorithm. In other words, we simply give the pseudocode for this algorithm. Suppose that we wish to show that the language L, which is the encodings of all J, such that J is a perfect square, can be accepted by a Turing machine. We can give a high-level description of this Turing machine which accepts this language L as follows. On input J, the machine runs a loop for I equal to 1 up to J. It would square I and compare it with J. If I squared is equal to J, it will accept, otherwise it will reject. Notice that in this case, the description of the Turing machine does not refer to various parts of the Turing machine, the tape or the head or anything like that. What I have done is simply given you pseudocode of an algorithm. Notice that in this case, I'm assuming that we can make a Turing machine do various things, such as squaring an integer or comparing two integers. Well, the thing is, I'm completely convinced that this high-level description can be converted into implementation level description first, and from there eventually to a formal description. The Turing machine that I have described using this high-level description will eventually have hundreds of states, but it can be described formally. So from now on, we will prefer these high-level descriptions of Turing machines, but you must keep in mind that every time you give a high-level description of a Turing machine, you must be completely convinced that you can eventually turn that high-level description to a formal description, possibly by first converting it into an implementation level description and then converting the implementation level description into a formal description. This is the same thing as we do in our algorithms courses. For example, when we describe an algorithm using pseudocode, we are completely convinced that by spending some amount of time, we can convert that algorithm into a program. Similarly, in this course, when we describe a Turing machine using a high-level description, we should be completely convinced that we can convert the high-level description eventually into a formal description. Well, today we have looked at various aspects of Turing machines again. We have formally looked at Hilbert's 10th problems. We have looked at the concept of encodings and so on and so forth. And we have also looked at how Turing machines can be described. From now on, we have agreed that all our descriptions of the Turing machines that we will describe in the rest of the course will be high-level descriptions. You must make sure that you understand how to convert these high-level descriptions into formal descriptions. I'll see you next time. Thank you and goodbye.